So good morning, everyone. My name is Edward, and today I'll be discussing my thesis that I've been working on for the last while, and it'll be on topic of empirical design rules for binder jetting additive manufacturing. I was supervised by Professor Meyer and Professor Vazia, so thank you to them for their support along this journey. So to give an outline of what I'll be talking about in today's presentation, it'll be broadly divided into the four general topics: methodology, analysis, and the conclusions. But more specifically, this gets split up into some discussion about what binder jetting additive manufacturing is, looking at the methodology for the experimental work I did, and how I designed and printed the artifacts, and then the analysis I performed, measuring the features on those artifacts, and then proposing some design rules, along with some conclusions specifically on how this evaluates in the broader context of other research. So for anyone not familiar with additive manufacturing is a process defined by ASTM in one way as the process of joining materials to make parts from 3D model data, typically in a layer by layer way. It's usually in contrast to conventional subtractive manufacturing techniques. So additive manufacturing is different from what you would see with CNC milling or conventional milling, where additive manufacturing is taking a digital file and building up from the raw material rather than taking a large piece of material and subtracting it. So this is informally also known as 3D printing and encompasses quite a variety of different technologies. So things such as laser powder bed fusion, fused deposition modeling, selective laser sintering, all of these are examples of additive manufacturing. And the one I'll be discussing today in specific is binder jetting. So what is binder jetting additive manufacturing? It is, like I mentioned earlier, like many other AM technologies, it works with a layer-wise printing process and a powdered material. And it takes the powdered material and combines it with a liquid binder to form the shape during the printing process. And afterwards, post-processing is required to take that printed part and densify it and give it the desired mechanical properties. So a broad overview of what this looks like in 4 stages is, first, the part is printed in a powder bed. So in here, the green area represents the printed part within the gray powder bed, and that creates our desired geometry. After that, the entire powder bed is cured to partially strengthen the parts and create what is known as a green part. So a green part is a part that has been cured and has partial strength, but it's not quite at the full strength. So it has roughly the strength of what you can imagine it to be as chalk. So it won't hold up to any physical uses, but it is strong enough to be depowdered and extracted from the powder bed. And once the green parts are extracted, typically they undergo a sintering process to densify those parts and make them into solid metal. There's other alternatives as well, but typically sintering is used with our machines in the lab. So looking at just the printing process itself, how that works is that it's a layer by layer process. This diagram goes over the 8 steps, but generally the way it works is there's a powder bed, it moves down by 1 layer, a fresh layer of powder is deposited on top, in this case by a hopper, and a roller is then passed over it that rotates to compact it into a dense layer. And afterwards, a print head passes over and deposits droplets of binder. Typically, this is a print head as something you would see in an inkjet printer, working on piezoelectric or thermal properties. And then lastly, a heater lamp passes over the print bed to partially evaporate the binder. So this is just one example of how binder jetting can be done. There are other ways that this has been implemented in different manufacturers' machines, but this gives an idea of what it looks like. So this is a quick video of the process, has been sped up a little bit for time, but the idea here is you just saw it deposit the powder, and now it's going to go through and perform the spreading and the compacting using the roller. After this step is done, the print head will pass over it and jet the droplets of the binder. So what you'll see here as it passes over is that there'll be darker areas. These represents the areas where the binder has been jetted and will be part of the final desired printed parts. So why are we interested in binder jetting as a technology? It has a few advantages. So it's fast for mass production. As you saw, each layer can be performed relatively quickly. We're not depositing material one by one. We're doing kind of a mass sweep across the bed. It's relatively cheap compared to other additive manufacturing technologies, and there's a wide material compatibility. So it works with typical materials such as stainless steel, but also copper, which is highly reflective and has challenges with other additive manufacturing processes. It works with ceramics, and it also works with casting sand. The reason for all this is mainly because binder jetting doesn't involve significant amounts of heat or energy within the printing process. So the printing process can happen in an ambient atmosphere without needing a sealed off environment where the melting of the metals can happen. So one other advantage of this is that it has a greater design freedom, and that leads into what I want to discuss for my thesis today. So to take advantage of this design freedom, and generally within additive manufacturing, industry and academia have put together several design guides and design rules to establish what can and cannot be built using additive manufacturing. So to differentiate the two, I define based on the literature what design guides are they are general language-based recommendations. So this is things such as don't avoid sharp overhangs in your part when you're designing them, avoid sharp corners, avoid excessive overhangs. They're general and they're very broad, but they're still useful. However, what I want to get into now are design rules. So these are much more specific numerical representations of what can and cannot be manufactured. So for example, if you have a thin wall feature, a design rule would be thin walls must be greater than 0.5 millimeters to be reliably manufactured. So this is a bit more concrete, a little bit more useful for testing whether or not a mechanism or a part can be successfully manufactured. Both of these are dependent on process parameters and the chosen materials, and they're also specific to the AM technology. So for example, design rules and guides developed for, say, fused deposition modeling would not apply to binder jetting and so on and so forth. So there is a need for each AM technology to have its own set of design rules and guides, and these tables summarize a few of them and are out in the industry. So how do we go about developing these design rules and design guides? One way is using benchmark parts. So benchmark parts have been used in the past to compare different additive manufacturing processes against each other, and they can also be used to develop design rules. They typically are designed to have a variety of different geometric features and sizes on them, and they're typically targeting types of features that are difficult to manufacture for an additive manufacturing technology. So things such as very detailed features, overhangs, slopes and curved surfaces, thin walls, like I mentioned, and small diameter pins and holes are typically things that most additive manufacturing technologies find challenging, and that's why benchmarks usually include a variety of them to see what are the limits of this technology and how it can be printed. So this kind of brings us to the motivation I have presented for my thesis, which is exists at the moment a gap in these detailed design rules for binder jetting. So for other additive manufacturing technologies, work has been done to develop these design rules. Binder jetting, specifically metal binder jetting, lacks these data-based design rules. This makes design for additive manufacturing, specifically for binder jetting, challenging, as evidenced by these photos. In the top right is a part that I tried to design and print earlier this year, and it was designed to be a compliant flexure mechanism, but unfortunately it broke during the depowdering stages because I didn't know what the limits were for printing. Similarly, at the bottom there, this is something from literature that was published recently. There was a group that was trying to manufacture boron carbide collimators for neutron scattering using binder jetting, and they also ran into issues where they had thin-walled features that were cracking during their printing process. So there exists a need for researchers to understand what can and cannot be printed so that they don't waste unnecessary time, energy, trying to redesign and iterate through parts when instead a design rule could have established what were the limits when designing. So to summarize, what I want to do with my thesis is our three research objectives. So the first is I want to propose a workflow to be able to generate these design rules for binder jetting. Secondly, I want to establish these design rules using this procedure for a specific set of features under certain conditions. So for my thesis, I focused on the green parts, so the parts after they've been printed and cured, but before they've undergone further post-processing to become fully dense metal parts. The reason for this is that sintering and other heat treatment introduces other effects that affect the geometric and print quality, and I wanted to kind of leave that out for now since that's been considered in other work that's ongoing. And I also limited to a specific material and specific set of process parameters just to keep it within the scope of a thesis that can be completed in a reasonable time frame. And lastly, I developed a procedure to also expand just beyond just design rules into actual compensation factors that can improve the printed dimensional accuracy by compensating for it in design. So now looking at what I did in my experimental work, This flowchart goes over pretty much the entire pathway I use to generate my data and come up with my design rules and compensation factors. So first, I designed certain artifacts that chose certain feature types, dimensions, and orientations. Once those are designed, I ran those files through the printer to generate the parts using a specific set of configuration and process parameters. Those parts were then cured and depowdered, and then imaged to do feature analysis using computer vision to determine what features printed successfully and the degree to which it's printed successfully. And then from there, the outcomes can be analyzed using these performance maps, and compensation factors can be generated from looking at the dimensional accuracy. So jumping back to what the artifact design process was like, I designed these artifacts to determine minimum feature dimensions as the target for this thesis. And I chose 4 types of features based on what I had seen in the literature and what I knew from prior experience with binder jetting to be difficult types of features. So these were thin walls, thin gaps, vertical gaps, and through holes. And what I varied for each of these features was the feature dimension. So the nominal feature dimension, as seen in here, is, for example, the thickness of the wall. I also varied the part thickness. So the context in which a feature is being printed, in this case, will be the thickness of the entire part. And that was also varied for some parts to see how that affected the printability and error. And lastly, the orientation, which I'll go over into more detail in a later slide. So this is an image of each of the 4 artifacts I used to determine minimum feature sizes. So for thin walls, thin gaps, vertical gaps, and through holes. And these are the types of nominal dimensions and part thicknesses I chose to look at for these features. So going back to what printing orientation means, so each of these different artifacts was printed in a few different orientations. The reason for this is as the orientation of the part changes, so does its position change relative to the print bed and the machine itself. And I know from experience that the printer does not behave the same in all the axes. For example, in the x-axis, we have the powder spreading happening with the roller, but orthogonal to that is what the print head is jetting. Similarly, in the z-axis, that's where each of the layers are being deposited. So each of these 3 axes are being treated in unique ways by the printer. And so to examine what's happening there, I adjusted the orientation of the parts that were printed. Moving past just the minimum feature sizes, I also took a look at the clearances between parts. So this is looking at if we want to print an assembly in a single run, if we want to be able to separate those individual parts afterwards, what is the minimum clearance that's required? So this is important for assemblies and for articulating surfaces. To examine this, I designed a part that had cylinders with a 10mm diameters that were placed within an outer wall, and I varied the different clearances between the cylinder and that wall. So as for the printing itself, for the main collection of specimens, I used the X1 MFlex machine, which is in the MSAM lab, with a custom reduced build volume. So the reduced build volume helps reduce the amount of powder and time required for individual smaller prints without having to use the full size build volume. The dispensing configuration was the hopper, which is what I showed earlier in that slide. And the material was 316L stainless steel powder with a 15 to 45 micron powder size distribution and a spherical morphology. So they were all nice round spherical particles that were well suited for this process. I used the X1 aquafuse binder as well that was provided by the manufacturer. And on the right side is a table that summarizes some of the other relevant process parameters that were used. So beyond just that main collection of parts, looking at the features, I also want to take a peek into what are the effects of process parameters on printability and geometric error. So I want to examine what was happening with the dispensing configuration. So besides using just the hopper to supply the powder, there is an alternate configuration where the powder is being supplied by a feed bed that moves up as the printing goes on. I want to see if there was a difference in that. So I printed a subset of parts using that configuration as well. And for bed temperature, I wanted to see if that heating that happened between each layer affected the printability of certain features as well. So I looked at thin gaps and checked it against 2 different temperatures to kind of see if there's any indication of something happening there. So this is a video of what that looks like in fast motion. This is a time lapse of some of the parts being printed. You can see each layer, there's powder goes down, the binder is deposited by the printhead, and this happens over and over until the part is completed. So as for the curing and the depowdering, all these parts, once printed, were cured at 108 degrees Celsius for 12 hours under open atmospheric conditions, and then they were left to cool to room temperature before depowdering by hand using a set of tools. So once this was complete, these are now green parts that are still fragile, but left as is for the analysis. There was no further heat treatment done at this point. So for the feature analysis, what I chose to go with was using backlit images of the parts using a microscope. In this case, it's the Keyence VHX7000. And the Keyence provides image stitching and focus stacking to improve the quality of the image as well. And the reason for the backlit images is to highlight any areas that may have not had powder removed. So I want to make sure that if a feature is successfully printed, that it is visible from the top through the bottom, and there's no excess powder that will be seen by blocking the light. Afterwards, I used a computer vision algorithm to analyze these. And the reason for that was to have a repeatable process that can be replicated elsewhere, but also to allow for things to be sped up with multiple measurements from a single image. The reason in general for going with an image-based approach as opposed to a traditional coordinate measuring machine or just using a pair of micrometers is because the green parts are so fragile. If a physical measurement technique was used, there's a good chance that it would either A, damage the part entirely and break it off, or B, affect the measurement as it's being pressed against the feature. It would adjust the measurement simply by measuring it. So this provides kind of a non-contact approach that eliminates those risks. So to do this, I built a software tool that I wrote in Python. It is open source. It's available on GitHub for anyone who's interested. And you can see the video of going through it here. It takes in those part images from the last step as the input. It provides a series of computer vision operations to generate a comparison to the digital CAD model. And then it highlights the parts that are different from the CAD. So what you'll see coming up is the alignment. And this is going through what it finds differences as. And then it also does a measurement of features using a fitting algorithm to see what the best fit would be for a given feature. So these lines represent those types of fits. So the computer vision algorithm itself is described in these steps, where the original image is taken, steps are taken to convert it into a black and white image where the part has been separated out from the background. And once that's been done, a slice is generated from the CAD file as well, and that is compared against the image that's been extracted. And once that comparison is done, I can now see what the differences are. So the underprint, for example, we can see that these two walls on the far left, they didn't print successfully, and they show up on the underprint as areas that are missing. And similarly for all the rest of the walls, we can see that the overprint, as the walls are larger than expected and predicted by the CAD model that we generated to print these. So beyond just comparing against the CAD model, like I mentioned earlier, I also took these individual features, I cropped them to focus on each one individually, and performed an analysis to see what will be the best measurement to represent that dimension. So for both the linear type features and also the circular ones. So now the experimental work has been completed for the most part, and now that what's left is to do the analysis on the data and determine what the outcomes were. So first, I'm looking at whether or not a feature was successfully printed. And to do that, I based off the coincident area. So the coincident area comes about from taking what was printed, comparing against the nominal area from the CAD model, and looking at the overlap there. And that overlap is used as the coincident area. And that percentage is generated to figure out whether or not that part was successfully printed. So for example, in this image here, on those far left, those two walls that didn't really print at all, those will be categorized as success since there's almost no overlapping area. Whereas in the middle, there's one that has most of the wall printed. That will be classified as a partial success. It's still mostly there. It's missing a little bit. And that on the far right is a full success. The entire feature is there. It is overprinted, but the entire feature, as predicted by the CAD, is there. This nominal area is based on whether the feature is negative or positive. So for positive features, like the thin wall artifact, we're looking at where the material is. And for negative features, like the holes and the gaps, we're looking for areas where the feature should be clear. There should be no material in a specific area. I chose these ranges to classify the fail, partial success, and success ranges. So now looking at the results from the thin walls, what I can notice is that the orientation does play a role in whether or not it prints successfully, particularly for thin walls. And for thin gaps, orientation also plays a role. But another interesting effect that comes about is there's no full successes noted for the thin gaps. It's all only partial successes. So this is going to be relevant later on, but something about the negative features, the thin gaps, doesn't lend them well to a success. Moving on to looking at the vertical gaps, again, these were affected by the part thickness. So the thicker the part got compared to the 1 millimeter thickness and the 5 millimeter thickness, we were seeing worse performance in terms of actual features coming out. And the reason for this, I propose, is that there is a increased difficulty in depowdering the features as they get thicker. The reason for this is, one, there's a larger volume of powder that needs to be successfully removed. And secondly, it becomes more difficult to access the interior of these features as the part gets thicker. So moving on to through holes, again, there's a similar effect happening where the part thickness is affecting the success rates of the features. So as, again, the part thickness increases from 1 to 5 millimeters, we're seeing worse performance in these through holes. Also seeing that the orientation affects the through hole printability as well. So one reason for the part thickness that comes about from these features is there's a possibility of binder imbibition being affected by the number of layers. So for certain orientations, as the number of layers increases, that's what's required for a thicker part. And each layer presents an opportunity for binder to be jetted improperly, for the liquid to behave in a stochastic way and kind of spread out further than expected. And this would, multiplied over more and more layers, increases the odds that something went wrong and the part didn't complete successfully. And now looking at the clearances, after printing the parts, I separated out the ones that could be removed and the other ones were still stuck inside. And this is a success map of that, looking at which ones were removed successfully. So moving past just whether or not it feature prints, I want to look as well at the dimensional error, looking at how much do these deviate from what we expected when we designed these parts. So looking at the thin walls, I performed a linear regression and found that the nominal feature size dimension and the orientation of the feature did not impact the dimensional error in a significant way. However, it can still be approximated as a single value to represent what this error is in all cases. So something to note here is that the error is positive. It's 0.3 millimeters approximately oversized, and they're always going to be oversized for this type of feature. Similarly, for thin gaps, it could be summarized as a single value to represent that error for all the different features and how they came out. And in this case, the thin gaps are always undersized by approximately 0.3, 0.4 millimeters. So what we're seeing here is that we're always seeing excess material on these parts. The parts are always coming out with the excess material condition that the gaps are smaller and the positive features are larger. For vertical gaps, things get a little bit more confusing. There is a significant effect of both the nominal feature dimension and the part thickness on the error. And for these, the error actually crosses over from both negative to positive. So this is possibly due to the fact that these were printed in that vertical orientation. We're seeing some different effects happening from that as well. And as for the through holes, these were dependent on orientation and part thickness, and the linear regression is as follows, showing the effects for that. So moving past just the features and move on to the effects of some of the process parameters. For the bed temperature, I was looking at the thin gap artifact and adjusting the amount of heating that happened between layers. And the effect I was seeing is that the dimensional error gets worse as the bed temperature is lowered. So in this case, what I noticed is that the heating is impacting the binder evaporation and curing after each layer. Without sufficient heating, that binder evaporation is not occurring as it should. The binder is remaining liquid and infiltrating further into the part than it should. Typically, the heater would prevent the binder from going too far. Each layer would stack up and be kind of frozen in place with the heater. But if they don't get sufficient heating on each layer, then dimensional error stacks up as that binder liquid just seeps further into the powder. For the dispensing configuration, so comparing the difference between the hopper and the feed bed, for the thin walls, it was theorized that there could be an impact on dimensional accuracy due to the powder bed density that's affected by these different configurations, but there was no noticeable effect for thin wall features. However, for through-hole features, there was a significant effect. So something is happening here. There's a contradictory result in possibly, but I'm theorizing it might be because the earlier one, the thin walls, is a positive feature, whereas the through holes is a negative feature, and that could be impacting why we're seeing it only on one type of feature. More work needs to be done to examine this effect. This isn't conclusive, but it is suggesting that there is something interesting happening here. So taking all that into account, I want to now propose some design rules. So walking through an example of one of these design rules is a thin wall feature. So for example, the one here in the top left, 1.1, I can say a design rule as for a thin wall that is aligned in the x-axis as shown in the image, that is 5 millimeters high, the dimension of the wall, dimension D, must satisfy a constraint of it must be greater or equal than 0.3 millimeters. So this was based off the success maps from earlier, and I've gone through and stated design rules for each combination of features and orientations. Similarly for the through holes and for the clearances as well. And as a reminder, the orientation is impacted by its position relative to the printer, which affects the print powder spreading direction and the printhead jetting direction. And now for the compensation factors. So the goal for these compensation factors was to generate a value that can offset the effects of this error. So for example, if we printed a model that had a thin wall of 0.5 millimeters thick as designed in the CAD, it would come out as predicted to be 0.8 millimeters once printed. If a designer can go ahead and anticipate this by generating that offset and applying it beforehand, so the model is designed to be 0.27 millimeters thick. Once printed, it should come out to be closer to the desired accuracy and desired feature size. So all of these compensation factors can be generated from the linear regression models from earlier, which are again dependent on which feature you're looking at, the nominal dimension of the feature, and so on and so forth. So to start wrapping everything up, what have I done in my thesis? Firstly, there is this procedure that I'm proposing and use to generate design rules and compensation factors. It goes through choosing a set of features and orientations that need to be examined, designing those parts, fabricating them using a set of acceptable process parameters, generating measurements using backlit images. Other measurements could also be applied to, depending on the AM technology, synthesizing all that information into a set of performance maps and a linear regression model that can be used to create and state these design rules and compensation factors. So referring back to the research objectives, which were stated here, I set out and accomplished all three of them. So to summarize, this demonstrates that procedure, and I also noted various observations on the effects of different process parameters, part thickness, and feature dimension. Some of the notable findings is that part thickness does impact dimensional accuracy quite significantly for some types of features. The bed temperature plays a role in the accuracy as well. The features are always nearly always printed with the excess material. And something that was noted just during the experimental work is that the depowdering and the strength of the features and whether to hold up to depowdering seem to be the limiting factor for what can and cannot be printed. So why is this work important, and why should anyone in the industry care about this, or anyone in academia even? Well, there exists an opportunity I stated earlier where there's a gap in design guides for binder jetting compared to other technologies, and this provides a stepping stone towards filling that gap and fleshing it out for users and designers. In fact, there is a technical standards committee at ISO ASTM that's working on stating these binder jetting design guides and rules, and work is ongoing in that. It also complements other active research happening at Waterloo and other institutions to look at what's happening during that post-processing step with sintering and the heat treatment and how that affects geometric accuracy as well. So again, this work is limited to just the one material class and selected printing parameters. And again, the depowdering method is depending on the training of the operator and other factors, such as their level of experience and the tools they have available. Additionally, there are manufacturing challenges where there are only a certain number of parts that can be manufactured within a certain time frame. Again, we have finite resources, so we couldn't do everything we wanted, but we did enough to confidently state some of these design rules and be sure that our process works. So the future work using this as a starting point is continuing with these same parts to do that sintering step and see what happens afterwards with the geometric accuracy there. So there's a whole another set of simulations and processes that are happening in that step that could be examined. Another thing that could be interesting to note is that maximum feature size becomes a role now once we're looking at the post-processing. There is a maximum feature size for binder jetting where if it's too large, it won't sinter properly and the binder won't be successfully extracted as well during the heating. So that's something to be considered as well. The full process map, expanding this experimental design to kind of consider all the different factors in more detail, looking at different feature types, different orientations, different part thicknesses. So going beyond the limited variables I chose in this one and expanding it out to get a very full set of design rules. Investigating the effects of different process parameters, like I mentioned, the bed temperature and the configuration of the power dispensing played a role, but that could be investigated in its own study as well. And also expanding this to just other types of materials. So looking at irregularly shaped powders, such as water atomized powders, other materials, not just looking at maybe stainless steel, but also looking at perhaps more exotic materials like silicone or copper and seeing if that impacts these design rules. Beyond just the experimental work in that sense, there's also the tools that I started to develop, the computer vision algorithm that can be expanded further to improve its reliability and expand it to other types of features, as well as expanding it to actually do in situ monitoring. So this is an image of the printer as it's printing. If this computer vision algorithm can be coupled with the data from the printer as it's printing, then maybe there's an opportunity there to predict and qualify materials and processes and parts as they're being printed. So that's an interesting opportunity as well. If we want to go into machine learning as well, there is plenty of data being generated using this approach that could be used to model this printability in more detail. So rather than just looking at the matrix and design rules, it can get into more complex combinations that a machine learning model might be able to capture that would otherwise be difficult to do with just a simple set of design rules. So that concludes this presentation, and thank you all for listening. This is kind of an example of all the different parts that were printed and imaged over the course of this work. So thank you very much. And I'll switch over to audio now before we start questions, but yeah, thank you.